nearly exactly, where we were, or we are almost to where we were last year on July 11th, which is tomorrow. I think July 11th might have been a Monday last year, but still, we're almost where we were tomorrow last year. And bad news, there's a whole lot more slides than I thought we had, but it's fine, because it looks like I planned for this in the syllabus anyway. So, I don't have your practice exam done yet, but you will get that. I'll finish that today, so you'll get that, depending on how things go, sometime later today or maybe tonight. I will also, I'm gonna be throwing together kind of a, I'm just gonna go through your book and pick out a lot of the questions that I really like. But I'm gonna throw them on a worksheet just for convenience. You'll get that tonight too, tonight or tomorrow, just so that you have problems that I've picked out. I'm going to chat with my TA today, and hopefully I'll get his worksheet ahead of time with key. He will make a key beforehand. And you guys have a quiz tomorrow, right? Yeah, okay. So I will be making you guys a quiz, giving you some practice problems. One good resource for practice problems is going to be like the examples and the problems that are in our slides that we don't get to. Those are really good. In fact, I was going to make you a worksheet by just taking a bunch of those and like all of the ones from the slides and put them on a worksheet, but you can also just go through the slides and pick those out if you would like. That's a pretty good resource. Let's see. I think, yeah. Quiz tomorrow, quiz Thursday. They'll be open, internet, open everything, so make sure that you bring your devices and chargers and can access the textbook and your notes and everything on those. They'll also be 30 minutes, so I'm not planning on making them difficult to finish in 30 minutes. But it's open internet and everything, so like keep in mind that that takes longer, so you know what I mean, like study for an open book test because you don't just have like 12 hours to look everything up. Does that make sense? That's mostly what I mean. Okay. Yeah. Is that all the business meeting, business items? Okay. So, we talked yesterday, academically yesterday, about, which piece? That one, is that better? Okay, it's okay, everybody can still see, there's no light. We talked about addition of water to carbonyl groups. Wait, did I do? Okay, that's sent. So we talked about how we can do this. Basically, we have our, that's so much taller than I want to think that it is when I'm over here. We have our nucleophile, right? So just the oxygen, and it's gonna attack the electrophile, the carbonyl-carbon, and we get this. And we talked about how this is entirely reversible and how usually this side of the equilibrium is favored, right? And why is that?
Pi bond from carbon
Yeah, so the answer to most things on like what's favored in equilibrium is almost always energetic energy, lower energy, almost always. Unless there's some sort of like, well, this one isn't favored, but we get a bunch of this product, but that's because the reaction releases a gas, so you just can't go backwards. So we just end up with that, even though it's not favored. If it's favored, it's because something is lower energy. So, or more stable. So when we talked about the bond energies, I was giving a larger number for this, and I'm talking about lower energy. What I mean is that those numbers that I was giving you are how much energy it takes to break that bond, right? So in order to break this bond, these two bonds, you would need you would need less energy. Yeah, these guys take more energy, right? Yeah, the sigma CO bond. Sorry. Bond dissociation energies. We already had this open. There it is. Okay, yeah, so OC sigma is 350. OC double bond is 732. So our pi bond is higher energy to break, stronger than two of these. So if it takes more energy to break it, then it's lower in energy, like stability. Does that make sense? Did I like make all of that worse? Okay, cool. So, addition of alcohols. That's the next part we're going to talk about. And we're going to talk about a hemiacetal and an acetal. So, nucleophilic acyl addition of one molecule of alcohol to the carbonyl group is going to give you a hemiacetal. Hemiacetal is this. We've got, so back here we have a geminal diol. This is a diol. We've got two alcohols. Now we turn one of them into an ether, and we've got a hemiacetal. Specifically, so it's named acetal, which is not really nomenclature based on an ether. It's based on the carbonyl group, right? But it's named this because these hemiacetals, it's more important.
What if you could do as?
It's more important to us that this came from a carbonyl than that it turned into an ether, right? Because this is entirely reversible. We can, and basically in order to reverse, we can either kick off this or this, right? And I mean, we're not necessarily gonna be able to do either, just, we're gonna talk about how we decide how we do that, but like, hemiacetal, alcohol and ether, on the same carbon. So, if we've got an equilibrium mixture, our hemiacetal is not going to be favored, right? Much like the geminal diol, we're not gonna make a ton of this. Now, to do chemistry, we don't need to make a ton, right? If we're gonna do chemistry that follows after the hemiacetal, if we've got more steps after that, all we need is for some of it to happen, right? Because chemistry is like billions of stuff. It's just all statistics. Everything is just sort of smashing into each other. As long as something happens sometimes, if that can continue on in a productive manner to push out products, then eventually we can make all the chemistry do that. Yeah? There's an exception though. Hemiacetals are not going to be favored unless you make a 5 or 6 membered ring, because nature loves those. I don't know. They're just very nice and stable. They don't have weird strain like square. Cyclobutane or cyclopropane, like those are a lot of it strained. And 5-membered rings and 6-membered rings, these are all single bonded, right? So these aren't planar, these are like chair, boat, and the 5-membered rings are like a little, like an envelope, I guess? There's like, they're planar, and then at the point, it's up. Like, the whole ring is planar, it's laying on the floor, and then just one of those carbons is sticking up, like a little house, or an envelope. That was not, okay. So, D-glucose is a 6-membered cyclic hemiacetal form, so whenever you get to biochemistry, you're gonna have all sorts of these, and this is really the same as these. And you'll draw them similarly, and you'll draw them all sorts of other ways that have like right angles in them because biochemists. But you know better for when you get into biochemistry. You won't do what one of my friends did and pretend that carbons all go in a straight line, because they do not. Okay, so hemiacetal formation. Let's do this. We can have base catalyzed or acid catalyzed. And let me make sure that's where I have my hidden slides. Okay, yeah, that's right where I have my hidden slides. I just wasn't used to it that way because I didn't have my green square. So, sometimes we have base catalyzed, sometimes we have acid catalyzed. In this case, we can have either one. Okay, fine, we'll call it that. So, that's a base. This is the alcohol that we want to add to something. And the first step, well, of course, that's reversible and it's fast because we're just doing acid-base chemistry, right? We're doing this, and we get that. So now this guy is ready to do something. And we're going to give it one of is it best if I try to keep going this way and then this way and then this way? Or if I like this and another thing down and then over and like snake back and forth? Is that okay? Okay, I need like everybody participate in that. Yeah, I can follow a snake, or like, I would really rather you not. Okay, okay, cool. I had some I'd rather not, so let's just not do that. I'm gonna draw the carbonyl carbon, aren't I? We decided we like it when I draw that carbonyl carbon that we're doing chemistry to? Okay. So we've got this, and we've got that. And let's identify our electrophile and nucleophile, because electrophile, right? It's nice and easy and has 3 lone pairs and a negative charge on it. really easy to find right now. And then this guy, which so far has always been the electrophile, but there is carbonyl chemistry where that's not the electrophile.
So that OR is the nucleophile though, right?
What?
The OR is that's the nucleophile?
Yes, did I say electrophile?
Yeah.
Thank you. Yes, correct me on things like that. Words are difficult, and if I say the wrong word, you don't have to just like, oh, she means this in your head. Like, say it out loud because somebody else in the class is confused if I'm using the wrong word. Sorry, thank you. Nucleophile. Nucleophile likes the nucleus that's positively charged because it is negatively charged. Nucleophile, electrophile. Thank you. Here, I'm gonna do my... This red marker lead is really aggressive. Really aggressive. Okay. So, we do an attack, right? Nucleophilic attack. And then our attack is not finished until we fix the valence problem. So, that, right? Okay. Draw what you get from that. Yeah. We started with one negative charge over here. We end with one negative charge. We're doing it right. So we've got this guy, and we're not technically at a hemiacetal yet because that's not an alcohol yet. So let's do a real quick. And the way that we're gonna do this. So we're going to protonate this guy, and the way that we're going to do it is we are going to write it like this. We can put it up on. We'll write it over here. Another alcohol, right? We're not going to draw this, write this as if it's a mole of water. Because if we have water in here and we're trying to make the alcohol attack the carbon, we also have water, so water can attack the carbon, then we're just gonna get a bunch of things, like a whole mixture of things, right? Because you can get a hemiacetal, but you can also get a geminal diol, right, if there's water in there. So we're gonna draw it like this. And just a quick protonation, and I guess that's reversible too, but that's slower, and this is fast again. And then we get the need for lots of colors. And we made a hemiacetal. So, base catalyzed. That's really nice because we just do the attack. That's the first, okay, fine, I guess it's not exactly the first step, but we didn't have to do anything funny to this, right? Now comes the thing where when we do acid catalyzed, it's basically the same thing. It's just that if we draw this nucleophilic attack, we're going to realize we have to go back a step, right? So I'm gonna actually do that. Okay, yeah. So we start out with that. Well, okay, fine, I'll draw it. Have this. Two bonds. All right, I'll draw it like that. Bond. We've got that, and we have acid in here. So we're gonna write that as HA. And the first thing that's going to happen is this guy is going to protonate itself. All S-base chemistry is fast, and we get that. And I'm not really going to draw this because, okay, so when we're talking about acid in an acidic environment, I always say we can't have negative charges, right? Obviously, this guy's a negative charge, but like, we can't have negative charges on the stuff we care about. Yeah? So like over here, okay, no, that's fine. That base was already negatively charged. But yeah, stuff we care about. So if it's just an A or a B because it's generic acid, we don't count those charges. Okay, so this guy is going to be a pKa of -7 to -10. Real strong, right? Because what's hydronium? pKa chart.